and there might be other students watching on there. Is that how that works? Or okay, okay, cool. Yeah, I'm hoping some other students join. I like to keep the classes very interactive. So if nobody else, I don't want to be the only one talking, but if I have to do that, I'll do that, I guess. Yeah. Awesome. All right. So, hello everyone. Really excited to be teaching test prep on Take Lessons. I've been teaching piano now for a couple of weeks, and I'm really enjoying it. Yes, and my name is Ayush. I recently graduated from UPenn. Been through the whole spiel of preparing for college, taking SATs, ACTs. I've done some SAT, ACT tutoring in the past, so this is not completely new for me. But however, I'm really excited to be teaching you all math. Yeah, so we're going to jump right in with today's lesson. Today's lesson, I want to focus on polynomials and graphs. So polynomials, when you think of that word, right, you see the prefix poly, and that's going to mean multiple things, right? So in this case, poly means more than one, right? And and then in this case, we want to know what a polynomial is. So, okay, actually, to make this easier, I'm going to share my screen. And okay, once that shares, I have a paper here so we can kind of go over these basic terms, right? So a polynomial is any mathematical expression that consists of what we call coefficients and what we call variables, right? And it consists of multiple of them or a single one. So, for example, 5x, we see that that is actually classified as a polynomial. But in this case, we only have one term, so we call that a monomial. If I was to add more terms to this expression, right? So if I added another term like this, plus 5, you see there's no variable there, but that still increases this from, it's no longer a monomial. Now we have two terms, so we call that a binomial. And you can consider any greater number of terms, and we could keep going on and on, right? So a trinomial, if you could probably guess, that would consist of 3 terms. But in general, when we're talking about polynomials, we're talking about mathematical expressions which have multiple terms. Some terms may have variables, and other terms may just be integers or other numbers. Okay, with all of that said, you can do a lot of things with polynomials, and they show up in math in a lot of places, right? So for example, a polynomial might be used to describe some function, right? So here we have our first problem for today, which was pulled from an SAT exam. We have evaluate this polynomial, right? So 3x squared minus 8x plus 7 when x equals minus 2. So in order to do something like this, right, it's as simple as taking that value of x, which in this case is minus 2, and plugging it in for the x values here. So I know I can't reach you all directly, but I would at this point probably ask you all to try to solve this on your own. So I'll give everyone a minute to try to solve this problem. And this one hopefully shouldn't be too hard. Okay, so to solve this, right, all we have to do is plug in the value of -2. So in this case, we have 3 times -2 squared minus 8 times -2 plus 7, right? So this evaluates to 3 times 4 plus 16 plus 7, which is the same thing as 12 plus 23, which is 35. And that's how you would solve something like this, right? So you'd just be able to plug in x equals -2 and solve this. Okay, with that basic question out of the way, now we have to talk about a very important concept for when you graph polynomials, right? So in this case, we have a function. Like I described before, here we have a function f of x. And what that basically just is telling you is that plug in some value of x and get an output value. We usually call that y, and then you would probably graph that. And once you graph that, you will be able to see what this function looks like, right, on an xy plane in 2 dimensions. So as an example, we see we have this function, 3 times x minus 4 times 2x minus 1. If we wanted to graph something like this, right, we would probably just want to plug in some values of x and see what we get, right? So for x equals 0, what do we get? We get 3 times -4, that's -12, times -1, that's 12. So for 0, we would have a value of 12. We could do the same exercise for 1, 2, 3, and so on. So I should probably label this graph. And let's say, in this case, we probably get some kind of parabola, right? So let's just say we get something like this. When I say the word zeros, right, what I'm actually referring to is the values of x for which this function is equal to 0. So in this case, those are here, right? Those 2 points which I've labeled. If those are a little bit small for you, basically what I'm saying is where this parabola is going to intersect the x-axis. Those are what we call zeros, right? And they're very important because they tell us something important about the function, right? They may tell us what the overall shape of the function is. If we had, for example, more terms in this expression for f of x, we could have more zeros. And if we have more zeros, we'd have more bends in the function, right? So we could have, this part could go down, for example, something like that. Okay, but enough said about zeros in this way, right? So graphically, that's what a zero means, the points at which it is going to intersect the x-axis. So in order for us to solve, right, what is the product of all the zeros? Well, the first step is just to set this function equal to 0. 3 times x minus 4 times 2x minus 1 equals 0. Why did I do that? Because in this case, f of x is y, right? It's what we're saying y is. So if we're talking about zeros, we're just talking about values for which f of x over here is equal to 0, right? And those are the values where this intersection is happening. Now, 0 has a very special property in math, right? Anything times 0 is what? It's 0, right? And so using that property, we know that any of these terms could be 0. We have the 3 term here, right? And we already know off the bat that that one can't be 0. It's 3, right? Because there's no variable there. So we just cross that off. And the reason I could do that is you could imagine manipulating this equation and just dividing by 3 on both sides, right? Now, either x minus 4 equals 0 or 2x minus 1 equals 0, right? Or both. But in order to solve, we could just solve these 2 simple linear equations. X minus 4 equals 0 and 2x minus 1 equals 0. So in this case, x could equal 4 or 2x could equal 1, x could equal 1/2. So then we go back to what the original question has asked, right? And what has the original question asked? what is the product of all the zeros? So in this case, we have 4, and we have 1/2. So the answer is just 4 times 1/2, and that's 2. Okay, normally at this point, I would pause and ask if there are any questions about any of the things I just described, because we're going to do a couple of more problems that are a bit similar in flavor to this. So, yes. No questions yet. Okay, great. So we're going to do another question, which is similar in nature to this one. So we have the function g of x equals x minus a times x minus b times x minus c, right? And it's telling us that the zeros of the function, now in this case, we already have the zeros, right? The zeros in this case are, and I'll read them out, 5, minus 3/2, and 1/2. It's asking, the question is asking, what is a plus b plus c? So this is a different type of question, right? In this case, we kind of have to figure out how do these zeros, right, tell us information about this particular function g of x, right? How are they going to tell us what the values of a, b, and c are? Okay, well, if we look back at our previous question, all we have to do is realize that for the value k, right, to be a zero of any polynomial p of k, right, we would have the term x minus k. Okay, what am I saying there, right? What I'm saying is, okay, so if we go back and look at our previous question, we had x minus 4 as a term, right? And it turned out that 4 was a 0. So all I'm saying in this case is k would be 4, right? So 4 is a 0 of this particular function f of x in that case. Now we're asking, so a, b, and c, these would all be zeros, right? So for these to be zeros, it's simply just 5 minus 3/2 and 1/2 would be our 3 zeros. And those would directly correspond to the values of a, b, and c in this case. So all we need to do is just add, right? 5 plus minus 3/2 plus 1/2. And that turns out to be 4, right? Because it's just 5 minus 1. So does everyone understand how we solved this question? We kind of reverse engineered the polynomial in this case. Okay, so these just give you a sense of some of the flavors of polynomial questions, which you might see on the SATs, right? Or the ACT for that matter. You may see a question where it's like, given a polynomial, find the value of the polynomial at a particular point, right? That was the first question we did. The second question could be, given a polynomial, what are the zeros, right? And try to solve those. And then maybe do some mathematical operation with the zeros, or also known as the points where it's intersecting the x-axis, right? So in that case, that was problem number 2. And the third type might be something like, oh, in this case, we're given the zeros, reverse engineer and come up with what the polynomial actually is, right? And they may ask you to as well compute the product of those terms, right? So you may have to do some factoring and expansion, right? So x minus a times x minus b times x minus c. Clearly, we would get what kind of polynomial? Well, we would get something that's cubic, right? The reason we have something that's cubic is because we have 3 x terms. And so when you multiply those together, you get something like x cubed dot, 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 right? So something like x cubed and then a bunch of other x squared terms and then eventually a constant, right? Okay, but I won't go through that boring type of expansion right now because we do have one last question before I jump into some graphing exercises. Does anyone have any questions at this point? Okay, great, great. All right, so we have one more problem on this particular set of problems, and it's at the bottom here. And if that's a little bit hard to read, I will just read it out for you slowly. So we have this function, right? In this case, we've just changed the letters. S equals, in parentheses, t plus 3 squared times t plus 2 times t plus 1 times t minus 1, right? So we have it here, a coordinate plane where we have S and T, like that. So essentially, we've just replaced our typical XY plane, right? So we have values of X, which will be our values of T, and values of Y, which will be our values of S in this case, right? And this is being graphed, right? This particular function. So it's asking, what is the product of the unique, that's the key word here, t-intercepts of the graph, right? So sometimes you may notice that a function does something like this, and we'll see this in a moment when I go to the graphing exercise as well. But what I've drawn there is a function, right, a polynomial which kind of bounces off the x-axis. And when I say bounces off, right, what I mean is that particular polynomial does not fully intersect the t-axis here. Instead, it just bounces off, and it still is at a value of 0 equal to, at a value of whatever this value of t is, it's equal to 0, right? But it doesn't go on into the negative, it doesn't go on into this fourth quadrant, right? So again, in math, we have the first quadrant here, right? The second quadrant, third quadrant, fourth quadrant. That's for whatever reason, that's the labeling that people will use, right? And I'm using Roman numerals there to describe it. But basically, this is important to realize that this is what we call a repeated zero. What I mean by a repeated zero is if you have a term, like in this particular polynomial, t plus 3 squared, you'll notice this phenomenon where you'll have a repeated zero, a zero which technically shows up twice when you expand and solve this polynomial, right? But it'll bounce off of the x-axis like that. Anyways, we'll see this in more detail when we go into some graphing exercises. But for now, let's try to figure out what are the different t-intercepts of this graph, right? So clearly we have t plus 3 equals 0 as one of our terms. So t could potentially be minus 3, and that would be a 0. We have t plus 2 equals 0, t equals minus 2. Oh, but something interesting, right? We have t by itself. So t could also be potentially 0. Now, if you were clever, you'd probably just notice this right away and stop, right? And see. The question is actually just asking us, what is the product of the unique t-intercepts of the graph? Boom, we already have 0 here, right? So what's the product of anything times 0? It's 0. So actually the answer is 0. And it's that simple. But ultimately, we also had the t minus 1 over there, right, is equal to 0. So it's 1. So technically, the unique intercepts are minus 3, minus 2, 1, and 0. But again, the product of anything times 0 is 0. So our answer is actually 0 in this case. Okay, so that covers the basic questions which I wanted to cover about polynomials. Next, we'll jump into a few graphing exercises and things like that. And I assume we'll probably actually have a lot more time. So if anyone has any questions, please feel free to ask them. And in the meantime, what I will do is I'm going to stop my screen share and share with you all the graphing tool which I want to use. Okay, hopefully everyone can see my screen now. If you don't know about Desmos, I would highly recommend you check out Desmos whenever you have to graph something and you don't have a graphing calculator handy. It's a great website and it's free to use. So Desmos, this graphing tool is going to help us kind of investigate different shapes of polynomials and how they look, right? So let's actually get to a simple one first. So even before I do quadratic, right? Here's a simple one. Everyone should hopefully know from basic algebra, right, that x minus 4, something that looks like that, right, is going to be a line. It's going to be what we call a linear equation. And in fact, solving linear equations is a whole different topic, and I actually plan to host a class later on in April related to solving linear equations as well as solving systems of linear equations. When you have multiple equations like this, how do you try to find solutions which actually satisfy all the equations? And that's an important skill which you need to know for the SATs and ACTs, as well as, how do you take a word problem and convert it to one of these types of equations, which we call linear equations. But anyway, why is this a linear equation? Well, because it has a form, right? Y equals mx plus b. We call that form the slope-intercept form of a linear equation, right? To allude to some other things I may talk about. So I'll just go ahead and type that right into the chat. Y equals mx plus b. And m, right? M is going to be our slope, which in this case, you can see what our slope is. It turns out our slope in this case is actually 1, right? And in this case, b is our y-intercept, and you can see that that's negative 4. So I'm going to go ahead and actually show you what I mean here, right? So let me just do one thing. Just want to make sure my mouse is visible when I'm pointing. Is it visible? No, it's not visible. Okay, but instead, actually, I can use this hovering thing, so it'll effectively be the same thing, right? So we see that minus 4 is our y-intercept in this case, and that's what I mean when I say y-intercept, right? Where this line is going to intersect the y-axis in this case. And you can see our slope is 1, right? What do I mean by slope? It's the change in y over the change in x, right? So for every unit we go down 1 in y, we also go down 1 in x in order for us to stay down to the right, left in this case, right? So we went down to minus 5 and down over left 1 to minus 1. And that change in y over change in x is what we call slope. You may also hear it referred to as rise over run, right? Anyways, but in this case, the slope is 1, right? In order for us to stay on this line, we have to go up 1 unit and across 1 unit. So if you look here, we have 4, 0, right? That's our x-intercept. And if you look over here, we have our y-intercept. That's 0 minus 4. So you take the change in y, in this case it was 4, and the change in x, and that's 4. You divide 4 by 4, what do you get? You get 1. So that's how you derive the slope of a particular line. Anyways, with all of that said, what happens if we change this function around, right? If we change this, see what happens. The function still has the same slope, but it's just shifted down a bit because we changed only one thing. We changed the y-intercept. Going back to our topic of polynomials, right? We multiply this function by x. Boom, what happens? The shape will change drastically, right? What happened in this case was we took our first term, that first monomial which we had, x minus 9, and we multiplied it by x, right? What happened is we got a quadratic equation, an equation where x squared is the highest degree term. So hopefully everyone understands what I say when I say degree, right? Degree is just what exponent basically is the term raised to, is another way of kind of thinking about that, right? So in this case, what happened was we had, and this function would be the same thing as x squared minus 9, right? We had a parabola where x is squared and minus 9 is where this function is intersecting the y-axis. Okay, so with that said, right, you can imagine we can keep doing this exercise and we can keep seeing how different polynomials are going to change, right? So what happens if we multiply that by x? Oh, look, we have a cubic function now. A function where this function x would be the same cubed, as x, right? X to the power of 3 is the highest degree term. And you notice about this one, right? So this particular cubic function, we have the roots of this one, right? The zeros of this one are -3, 0, and 3. How would I know that, right? Well, that actually just reinforces the concept which we were talking about before, right? So if I just factor out this, right, and hopefully people remember how to factor something like this, right? So we had x squared minus 3. Well, to factor something like that, you just do x minus 3 times x plus 3, and boom, we're back to the function which we had before, right? It's x minus 3 times x plus 3 times x, right? And setting that equal to 0, we would get the zeros of this function, -3, 0, and 3. So that's just reinforcing the concepts which we saw before. You can see this is a typical shape for a cubic function, right? Why do I say that's a typical shape for a cubic function? Because you can see that there are kind of like 2 turning points, right? And that there are 3 zeros. But that need not necessarily be the case, but in this case and in most cases that will be the case, right? But anyway, we can keep doing this. We can keep multiplying by x, right? So what if we had x squared here? This is a quartic equation now, a quartic polynomial. And there are actually still 3 zeros, right? Why? Now this goes to that concept which I was talking about before, where a term or a particular zero might bounce, right? It might bounce off of the x-axis. And in this case, the zero that is bouncing off is this one right here at 0, 0, at the origin. You see this one, right? The -3, 0. It crosses the x-axis. And so does this one, right? The 3. Those are not what we call repeated zeros. They are not repeated because they cross through the x-axis. However, this one, where we have the term x squared, actually ends up bouncing us off. So we can do this bouncing type of thing again, right? So let's see. Do this. So we actually have a quintic polynomial here, and you can see it has a very kind of strange shape now. But what did I do? All I did was I squared one of those monomial terms, right? All I have to do is square it in order for us to have a repeated zero. And it's going to bounce off in the same way that that the origin did, right? So it bounces off in that same way. If I remove this part, we're back to a quartic polynomial, but in this case, we're bouncing off in the other direction. And if you wanted to figure these things out, right, for the exam, you usually will be given a graph, right, in most cases from what I've seen. But you can always try to sketch it out, right? And in order to sketch it out, you have to remember things about how these things bounce off the x-axis, right? If you have a term squared like this, you immediately know that it's not going to cross. It's going to bounce off. Okay. Anybody has any questions about any of these things which we talked about, some of these graphing exercises? Okay. If not, crystal clear. Perfect. Okay. So yeah, so we actually finished the main content. Normally I would, I love student interaction. I pause, I try to ask a lot of questions. I try to make sure everyone's trying to understand everything. Since I'm the only one talking, clearly we're at half an hour here and I've been talking for the whole time. So just give me a minute. I'm gonna take a sip of water and then we can do a few more practice questions. And we can do more practice questions related to different topics as well that are kind of related to polynomials. So. Okay, let's do a few more questions then, in that case. So I'm going to just pull up some examples which I've found, so just give me a minute. Okay. So I'm going to share again my. Sorry, I'm going to share again my other screen, which has the paper. Okay. Cool. So that should be visible now. And what we're going to do is we're going to do a couple, one or two more similar questions, right, as before. So here's the function. We have f of x is equal to 10x minus 3 times 4x plus 1 times 5x minus 2. Okay, so in this case, you can see we have three monomials, right? And the question is first, find the zeros, right? And then, what is the sum of the zeros? Okay. So in order to do this, right, we'll kind of follow the same formula that we've been doing all along, right? So we know by what's called the zero product rule, that's the formal terminology, zero product rule, I believe, or zero product property, that when you have multiple terms kind of multiplied together, any of them could be zero, right? In order for the product to be zero, any or all of them, right? So you can imagine this could be like 3, and this could be, or rather, sorry, what I mean is like this one could be 0, and this could be 3, and this could be 2, right? But if you take the product of all of those things, that's still 0. So that's what it means. But by that property, by that rule, we can just set 10x minus 3 is equal to 0, 4x plus 1 is equal to 0, 5x minus 2 is equal to 0. Okay, given that, we just have three simple linear equations in order to solve, right? So we just do 10x equals 3. So x equals 3 over 10 in this case. 4x equals minus 1, so x equals minus 1 over 4. And 5x equals 2, so x equals 2/5. And now it just comes down to some fraction math, which is always an important skill for you to do. What is the sum of the zeros, right? So we can immediately see that 20 would work as a common denominator, right? So we'd have 6 over 20 times 2 times 2, and then minus 5 over 20 for 1/4, and then plus, and then in this case times 4, and then that's 8 over 20, right? So hopefully everyone sees how I did something like that, right? I saw that 10, 4, and 5 have a least common multiple of 20, and we would just be able to multiply this one by 4, this one by 5, and this one by 2 in order to get that. And in this case, once we add those three things together, we have 9 over 20. So final answer. Cool. So that's basically how this one went, and it's similar to the concepts that we had before. Let's get some more interesting questions. So I'm going to try to find some more polynomial related questions. So give me a minute here. Okay. So here we go. Okay. In this question, we're going to practice some skills for simplifying expressions, which basically are polynomials, right? But we need to do some sort of combination of terms, right? So let's try something simple here. 3x plus 2 minus 2/3 x minus 1/4. Okay, and so we just need to kind of decide what is the simplest form for this particular expression, right? What is the simplest form? And so when I say that, right, it goes back to the simple concept in math, which is you're allowed to group like terms, right? You're allowed to combine like terms. So we factor out this minus 1 over here, right? And we do 3x minus 2/3 x plus 2 plus 1/4. How did I do that? Well, this minus 1 is in front of this term, right? So it gets factored in. So minus 1 times 2/3 x is minus 2/3 x. Minus 1 times minus 1/4 is plus 1/4, right? And we are able to group these like terms together. So that's immediately what I did, right? So the x terms get to go together, and the terms that don't have an x next to them, they get to go together. And we're allowed to simplify them, right? We're allowed to combine them. So 3x minus 2/3 x, well, how many thirds is 3? It's 9/3. So 9/3 x minus 2/3 x is 7/3 x, plus how many fourths is 2? 8/4. So that's 9/4. And that's it. 7x plus 9/4. No, sorry, 7/3 x plus 9/4, right? That's how you answer that question. Okay, let's do another one. So this time we'll have a quartic polynomial, and we'll have the following: 6t to the 4th minus t plus 1 minus 6t cubed minus 4t. And the task is the same as before. How can we simplify this particular polynomial, right? So immediately off the bat, you're looking at these terms and you see, are there any other terms with t to the power 4? No, there's only one, right? So that one is going to be by itself. Are there any other terms with t to the power 1? Sure, right? There's one over here. So we'll deal with that in a minute. And then are there any other terms without a t, right? No, it's only just the 1, right? And are there any other terms with t to the power 3? No. So we factor out again this minus 1. We have parentheses here. So it's minus 6t cubed, right? Minus t plus 4t plus 1. Why is it plus 4t? Again, minus 1 times minus 4t inside, right? So we got 4t. And then all we have to do is combine. So the only things we can combine are the t to the power 1 terms. So it's 6t to the 4th minus 6t cubed plus 3t plus 1. And in this case, that would be our final answer, right? So we'd have a quartic polynomial, a polynomial where the highest degree term is raised to the 4. So again, that word, right? Degree. So the degree of this polynomial is 4. Why? Because the highest power, right? The highest exponent which you see is a 4. So that's why the degree is 4. So for this particular polynomial, this is the expression which you get. Okay, cool. I think we should do some other exercises, right, which are kind of related, right? Topics which are related to this. So I'm going to do something important, which is factoring, right? I think factoring is always a very important skill. And it's related to this because remember what I said before, right? Normally when you learn factoring, you talk about quadratic equations, right? Quadratic. Quadratic equations are equations where degree 2 is true, right? Where the highest degree term has degree 2. So in this case, for example, you could have x squared minus 9 is equal to y, right? That's a very important form for a quadratic equation, right? And to factor this is another way for us to obtain the zeros, right? So you can kind of do two ways, right? And both are mathematically equivalent. So one way is x squared minus 9 is equal to 0. X squared is equal to 9. So if we take the square root of both sides, we do the plus or minus square root on this side, right? We'd get x equals plus or minus 3, right? So those would be our two roots, either positive 3 or negative 3, right? But another way you can do it is to factor, right? To factor. And factoring just means breaking down something that's kind of more complicated, right? Into a product, right? Of simpler terms, right? So when I say product, again, I mean one thing multiplied by something else, right? Multiplied by other things possibly as well. And so in this case, we have x minus 3 times x plus 3 is equal to y. Oops, I ran out of room there, but you get the idea, right? So x minus 3 times x plus 3. And how did I get that, right? Well, this is something that I recommend that everyone should memorize for the SATs, right? And ACTs. When you see something like this, right, where you have x or any other variable squared, right, and you have another term which is negative, but it is, you know that it's a proper square number, right? So when I say square number, I mean any integer squared is equal to that number, right? So for example, we could have had a 4 there, we could have had a 16 there, right? Because 2 squared is what? It's 4. 3 squared in this case is what we have, that's 9. 4 squared is 16. 5 squared 25, so on, right? So of course it's important to kind of memorize and be familiar with the basic square numbers as well. But you could see a 144 there, for example. That's 12 squared. But anyways, based on that, you would know that this is a particular form for factoring a quadratic equation, right? And it always is the case that a squared or x squared or anything minus a square number, you can factor it like this into product of two terms, where the first term is x minus the square root of this term, so in this case 9, and then x plus the square root of the second term. And if we expand this, right, we can see that that's true. We get x squared plus 3x minus 3x minus 9 equals y. What happens with those 3x and minus 3x terms? They cancel out. So because they are plus 3x minus 3x. So we would just end up with x squared minus 9. So yeah, factoring is a very important skill. There's many ways to do this. And this is just a preview because in one of my future classes in April, hopefully we have a lot more students who are able to join. But yeah, in those classes, I'll be going into more problems related to quadratic equations, right? And factoring is usually the first step whenever we're dealing with quadratic equations, right? Because, okay, so sometimes quadratic equations, you can't actually factor them, right? Or they're hard to factor, or maybe, you're running out of time or whatever, anything. There's other ways you can solve them, right? And try to figure out the solutions. We'll go into that as well, right? You may have heard about the quadratic equation, for example. That tells you how to find those solutions, right? Those values of x. But it tells you to do it using an equation, right? So you just have to kind of plug into the equation the values which you know and get a result. But another way might be trying to factor it and in that way trying to solve. So there's multiple strategies for doing that. Okay, but enough said about factoring, right? Another important topic is linear equations. And we talked today about polynomials, but remember, linear equations are just another type of polynomial. They just have degree 1. So let's talk a little bit more about linear equations. And we're going to do that by doing some more graphing exercises. And again, if anyone has any questions, please ask questions. Okay. So we're going to go back to the graphing calculator. Okay, so everyone should be able to see that. Just give me a minute. Okay, yeah, I can verify that. Awesome. All right, so we're back to this, and remember before we had a quartic equation, but we're not going to do that anymore. So Desmos is good because you can actually enter multiple equations, right? So here's one line, and here's another line. You may notice I did something, and I did it purposely, right? These two lines have the same slope, x plus 4 and x plus 3. You see that they have the same exact slope, right? But what's different about them? The y-intercept. So we have a y-intercept of 4 for the first one, and a y-intercept of 3 for the next one, right? And that brings about a very special property. When you have two lines which have the same slope but different y-intercepts, they are parallel. Okay, you see that they're parallel, right, to each other. They will never intersect. You could go on forever. I could keep zooming out. These two lines will never intersect, ever. So if the SAT says, right, given these two lines, are they ever going to have a solution to the system of equations? So when I say solution to the system of equations, right, I mean values of x for which both of these lines evaluate to the same value of y, right? They would intersect, they cross each other. The answer is no, right, in this case. Why? Because these lines are parallel. They never, ever are going to have an intersecting point. Let me give you a different example, right? Boom, all I did was change the slope. And now these lines actually intersect each other. So if the SAT asks you, what is a solution to the system of linear equations given here, this is a solution, 1, 5. Why is that a solution? Well, if you take the value of 1, right, and you plug it into the first equation, you see that 1 plus 4 is equal to 5. So that's the same value of y. Do the same thing for the second one, right? 2 times 1 is 2, plus 3 is 5, right? So again, the second equation also evaluates to 5. So in this case, this is a solution, right, to the system of linear equations, and this is an intersecting point. You could do this for any other slope, right, besides 1 in this case for the second line, and they'll always intersect at least once. You'll see. And in fact, if you change this right back to what we had before, you'll see first, so this is what we had before. You have two parallel lines. They'll never intersect, and therefore there are no solutions to the system of linear equations, right? But if you do something like this, obviously, right, you change them to be the same line, well, they intersect everywhere. And in this case, we would say something that these two lines have infinitely many solutions, right? There's an infinite number of solutions to the system of linear equations in this case. Why? Because this is a trivial case. They're the same exact line, right? And in fact, that's always going to happen, right? So if you have two lines which evaluate the same thing, they're always going to be on top of each other, right? Duh, right? Okay, so that's interesting. But what if we had more lines, right? What if we had more functions? So let's add another one. So what if we had y equals, 4x? Well, then the question could be asked that, do these three lines, right, do they have any point at which these three lines could be satisfied, right? Is there any point where these three lines could have the same y value? And actually the answer is no, right? Why? Because you can see that this line intersects this line once, the green line intersects the blue line once, the green line intersects the red line once, but there's never a point at which all three of them intersect. And so therefore there is no solution where all three of them have the same y value, right? So that's kind of like a preview for how systems of linear equations work, right? And there are multiple ways you can try to solve you can try to take y equals 4x, right? And plug it in and try to solve that way. You can try to combine these equations and try to solve. There's multiple strategies, right? So we won't get into the details in this class, but in a future class we will. Okay, enough said about that. There is another thing I want to talk about, which is perpendicular lines. So here we go. Here we have something interesting, right? We have the first line, which had a slope of 1, and it's x plus 4. And then look what I did. All I did was take the negative inverse of the slope of 1. So negative 1 over 1. And I got this function, y equals negative 4, x. And I could also do plus 4. That's fine. And so they intersect at 0, 4. But these two lines are said to be perpendicular to each other, right? Because these form 90-degree angles at the intersection point. And the reason we know they're perpendicular is actually we can just look at the slope, and you can just look at what I said was like the negative inverse, right? So what do I mean by negative inverse? So if we had 2 here, right, in order for these lines to be perpendicular, we need to have negative 1/2. That's what I mean by negative inverse, right? So you take that 2 we have in the first equation, you do 1 over that, because that's what I mean by inverse, so it becomes 1/2. And you take the negative of that. So that's negative 1/2. And in this case, that is going to give us 2 perpendicular lines. They have the same y-intercept, right? They have the same y-intercept of 4, but because they have slopes that are negative inverses of one another, they are going to be perpendicular. So this is an important property for everyone to understand. Perpendicular lines versus the same line in this case versus parallel lines, right? So parallel lines, they'll have different y-intercepts, but they'll have the same slope. And because they have the same slope, they will never intersect, and there will be no solution to the system of linear equations in this case. All right, so that reinforces all of those concepts. And again, these are all concepts that are related to the concept of polynomials, right? And you can imagine doing this for really any type of equation, right? So what happens if we have a quadratic equation and a linear equation? These are also, they also have a solution, right? And you can obtain the solution simply by graphing, right? So if you graph and you see the points at which these two intersect, those are the solutions, right? This particular value, negative 0.366 and 4.268, and this one over here, 1.366 and 7.732, right? So that's one. And if you had two parabolas, for example, these actually these ones intersect that easily, like that, right? So you have x squared plus 5 and 2x squared plus 4, and these also intersect. So when we say solutions, it's just any point at which they intersect. So SAT might ask you just to try to find solutions to any system of any type of equation, and you should be comfortable changing these equations into graphs, right? Trying to graph them out, trying to write them down, and try to find the points at which they intersect as well. But this all goes back to what we talked about today about polynomials. All right, with all of that said, that pretty much wraps up everything I wanted to talk about in today's class. I will be having, as I said, more classes in April. I'm trying to do a regular cadence of Wednesdays. Awesome, yeah. Thank you everyone for joining. So the next class, I'll be away next week. But the following week, I will have a class on Wednesday for sure at 6 p.m. Pacific, and it will cover, I don't remember which topic I scheduled, possibly related to linear equations, but you can always check my schedule. And if anyone needs one-on-one help as well, I also have one-on-one help for this subject, so for test prep as well as any other subjects. You can check out my profile. But yeah, thanks everyone for joining. And hopefully this lesson was helpful and reinforce your understanding of some of these concepts.